Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper, Charlie to friends, and I'm a theoretical physicist currently working as a university researcher over in the Helsinki Institute of Physics in the University of Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how things evolve, how things interact, cool stuff happening inside the universe. I love being a scientist, I love being a cosmologist, and I love chatting to you all about all of the cool stuff I get to work on. So for anyone who doesn't yet know, Cup of Cosmology is an interactive stream. The idea here is that you people can ask me anything you want about space, about physics, about cosmology, about academia, about Finland. You can ask me anything and I will do my best to answer. Now, as always, I will not necessarily have all the answers to your questions, but I will do my best to answer whatever I can. If you're a first-time viewer, welcome. If you're a regular, welcome back. Great to see everybody here. I see we already have some people in the comments coming in, tuning in, and of course, cat on the keyboard, which is why I lock my keyboard as soon as I start the stream, because I don't trust my cats. Okay, yes, I see we have some of the regulars here. We have Ange, Ben, James, David Howden, Pratt. Great to see you, Scott, and Jim. Very glad you could make it. I know it's really early in the morning for you, but great to have you here, of course. Okay, do you know you can hear us moving about and clicking things whilst the theme music is playing? Yes, I do, which is actually why my microphone is turned off until about 10 seconds before I turn the camera on. So you can only hear me for the last 10 seconds. And if I don't do it 10 seconds before I go live, I forget. There was one stream where I started muted and just started rambling until you all told me I was on mute. So yes, you do. I'm aware that you can hear me moving and clicking things. That's just for that, should just be for the last like 10 seconds before I actually start talking. So has it started getting warm here? Warmer than it was. It is no longer minus degrees. We finally hit 0 degrees, which, you know, I do like winter. So I'm not happy to see the snow go. But yes, it is getting slightly warmer. Okay, as some of you have noticed from the title, from the description, today we're not doing an Ask Me Anything. Today there is a specific topic. So as you've heard me mention on these live streams before, there is a way where you can all request a topic. If you go to cupofcosmology.com, you can request a topic. If there's something you want me to talk about that I haven't covered or that you want me to talk about more in depth, you can request it. All I ask in return is that you do a donation to a charity that I sponsor. There's 5 charities listed on my webpage. You can pick one. If you do ever request a topic, please get in touch first, because I might not agree to every topic. So you have to get in touch first, make sure I agree, and then we can go ahead with the process. So today we have a topic request, a topic that was requested by Jim here in the comments. So today we are going to do a topic request, which means I get to talk about the stuff that Jim's asked me to talk about. And it's a very cool topic, so I'm very happy to do this. So we're going to cover a lot of stuff today. Yes, thank you, David, for letting me know. It's I appreciate you letting me know that you can hear me. It's all part of the plan. It's all part of the system. But thank you for letting me know. So today we are going to be talking about primordial black holes, and specifically about 1 or 2 new observations that have brought primordial black holes back into the conversation. So before I jump into the new results, we've got to set the scene. And I have plenty of time to fill. So the way we're going to do this is, first I'm going to tell you what primordial black holes are. I'm going to tell you why you should care about primordial black holes. I'm going to tell you about how we try to find primordial black holes, how we haven't succeeded in finding them yet. And then I'm going to tell you about the new results that may or may not change this. And then we'll see what the future is for primordial black holes. So spoiler alert, just to get you hooked, there was an observation by LIGO, a gravitational wave detector, in November that has got scientists excited, especially people who work on primordial black holes. I am not starting with we found primordial black holes. That's not what I'm saying. Stay tuned for more about that. That's going to come about halfway into the stream. But first, we need to set the scene with what are primordial black holes. So as always, even if I'm doing a topic, this is an interactive stream, which means that you can all ask me anything you want. I'll try to keep the questions on topic today. If you ask questions that are not related to what I'm talking about, or not related to primordial black holes, I might not address them today, but feel free to ask your questions anyway. And as always, if you have questions about what I'm saying, if something is not clear, if you need me to explain something in a different way, just let me know. Otherwise, it's just me here monologuing like a supervillain, which is fun to do sometimes, but also the whole point of Cup of Cosmology is it is interactive. So even if we are doing a topic, you can jump in with questions at any point, or like not literally jump in. You can't ask to be put on camera, but you can join in the chat. It might be fun someday to do the thing of people asking questions actually get put on the camera as well, and then you can actually come and ask questions, and that would be a fun thing to consider one day, but not the format of the current streams. Okay, so we're going to get started with primordial black holes, and then we will go into new stuff. So before starting on primordial black holes, we should of course start with what are black holes. Black holes are massive objects in the universe. Yes, hello, Wata. I have a cat who's very interested in what is happening, but he's calmish. Okay. So black holes are regions of the universe that are objects in the universe that are incredibly dense and have a huge gravitational pull. And it's such a strong gravitational pull that nothing can escape a black hole, not even light. Now, we know that in the universe, nothing can travel faster than light in a vacuum. If you have a black hole, not even light can escape from a black hole. And because light is light is the fastest thing in the universe, in the vacuum of space, if light can escape, nothing else can. Now, a black hole is basically just this. It's just an intense gravitational field pulling everything inwards. Every black hole has an event horizon, which is kind of the border or the edge of the black hole, and it's the point of no return. Before you reach the event horizon of a black hole, you can still turn away. Once you cross the event horizon, you can never come back. The amount of energy you would need in order to turn around or just escape that black hole is more energy than what is available in the universe. So once you cross the event horizon of a black hole, you are never coming back. Now, we know that black holes exist. We have pretty good evidence for black holes. We've been able to take indirect photos of black holes. We even have a photo of the black hole at the center of our galaxy. I put it in quotation marks because obviously you can't actually see the black hole itself, but you can see all of the matter swirling around it about to fall into the black hole. So you kind of have a photo of the event horizon of the black hole in that you have a photo of all the matter swirling around and then a black thing in the middle. So black holes, regions of the universe that are super dense, huge gravitational field. Now, we know that there is a black hole at the center of every galaxy. In fact, there is a supermassive black hole at the center of every galaxy. There is an ongoing debate as to what was formed first. Did the supermassive black hole appear and then the galaxy formed around it? Or do you have a galaxy and it is so dense and so tightly packed at the center that things can collapse to form the black hole? So there is this ongoing debate as what came first, the black hole, the supermassive black hole, or the galaxy, but we know for sure that at the center of most galaxies, if not every galaxy, there is a supermassive black hole. So we're pretty confident that black holes are a thing that exist. But there are several different types of black holes we can talk about here. Just going quickly to the comments here, a question from James. Primordial black hole, dark matter, many things we can't detect, but they seem necessary for explaining things. Indeed. And these are potentially not as disconnected as you might think. We're going to come to that in a minute. But we're pretty sure black holes exist. We have a lot of evidence in favor of them existed, and we have found many times now black holes smashing together. We have evidence of black holes at the center of galaxies. Black holes we're pretty sure about. Question from Taz here, would it be valid to call a black hole an object or just an area in space and time? That is an excellent point. Either, depending how you want to define an object in the universe. If you define anything that has mass as being an object or a species or a thing in the universe, you can define a black hole as being an object. However, a black hole is also just a huge distortion of space-time, and therefore you can just say it is part of space-time that is hugely distorted, but usually we do think about it as being more of an object because it's something that has mass, and that is kind of how we define things in the universe of it has mass. Then you could get into the etymological debate or you know, the how do you classify things, and you'll never find a word that is good for classifying things because, you know, in general, humans are terrible at classifying things. But I think referring to a black hole as an object is a fair way of describing a black hole. Question from Prath, what is the reason we don't see, what if the reason we don't see what we define as primordial black holes is because all of them merge over time to form supermassive black holes? Excellent question, Prath. I will get to that later. That is a great question that I will be getting to. So most of the black holes that we think about, or the standard picture that we have for black holes, are stars that reach the end of their lifetime and collapse. Now, a star is basically a constant battle. Inside the star, you have fusion going on. You are building heavier elements. Hydrogen is fusing into helium. Helium is fusing into heavier elements. You have this constant fusion of elements getting heavier and heavier, producing bigger and bigger elements inside stars. This produces a lot of pressure. So inside stars, there's a lot of pressure pushing things outwards, but there's also a lot of gravity pulling things inwards. So all stars are constant battles of gravity going inwards and pressure going outwards. It's this battle. Once a star reaches the end of its lifetime, there are several different things that can happen, but for most stars, what is going to happen is the center of the star, at some point it runs out of fuel to burn, so the pressure becomes less. So then what happens is you have a dual process where the center of the star starts to collapse under the gravitational force. This causes a huge influx of pressure, which makes the star explode as a supernova, an exploding star. And then the core fully collapses into either a black hole or a neutron star. A neutron star is just a star that is extremely dense, but not quite dense enough or not quite massive enough to be a black hole. So our standard idea of how black holes are formed is a star reaching the end of its lifetime, exploding as a supernova, and collapsing to form a black hole. Now, this does mean that there are limits on the size of stellar black holes. I'm going to refer to these as stellar black holes, as in black holes that were formed in dying stars. Now, because we have a pretty good understanding of stars to some degree, we know that stars have this pressure and gravity battle. We know what goes into stars or how stars are formed. So we have pretty good understanding of what happens when a star reaches the end of its lifetime and it explodes and then it collapses. So this gives us kind of possible masses for black holes, stellar mass black holes. Now, we expect to find stellar mass black holes around 5 to 25 solar masses. So I'm going to be using this unit solar masses, which is just the mass of the sun. The sun is a pretty average star, so it's something that we can use as a good metric because we've measured the mass of the sun. You know, it's 10 to the 30 kilograms. That's a 1 followed by 30 zeros. That's how many kilograms it is. Instead of using that number, I'm just going to say solar masses. So most stellar mass black holes can be somewhere between 5 to 25 solar masses at the time of formation, or at the time when they've collapsed and you have them doing their thing. Then you can have neutron stars. If the star is not massive enough, instead of collapsing into a black hole, it could collapse into a neutron star, which is a star made entirely of neutrons held together basically by neutron degeneracy pressure, which means that neutrons can't exist in the same, can't be too close together, so that pushes things outwards slightly. So again, you have the battle of the neutron degeneracy and the gravity pulling things inwards. That gives you a neutron star. Now, due to how neutrons behave and how neutron degeneracy behaves, we know that neutron stars have to be between about 1.2 and 2.5, oh, I have a typo in my notes, 1.2 and 2.5 times the mass of the sun. So if you have a star that's reached the end of its lifetime and it's collapsed, what's left behind is a core. This core can either be a neutron star if it has mass of 1 to 2 solar masses, or a stellar mass black hole, which would have mass of 5 to 25. You might notice there's a gap there that is known as the mass gap in between like 2.5 solar masses and 5 solar masses. We don't really expect black holes to exist. And then you can also have, on the opposite end of the mass, like really high mass things, you can have supermassive black holes. Now, supermassive black holes can have anything from 120 solar masses upwards to 1 billion solar masses or 1 million solar masses. So you have these different mass ranges. That gives you a second gap, which is in the range of 25 to 125 solar masses. That is a region where we also don't expect to find too many black holes. Now, of course, one thing we do know is that black holes are going to merge together. I'll come back to the questions in a sec. I see there's a couple of very good questions. We'll be back there in a sec. So we know that black holes can merge together. If you have two black holes coming close to each other, they can start spiraling around each other. They come together. They leave behind one black hole that is bigger than the initial two were. Of course, it's going to be not bigger than the individual sum of the parts, but you end up with a black hole left behind larger than the black holes that you started with. So this is also a way that black holes can grow. Now, we know that there's a lot of black holes colliding in the universe, and therefore this allows you to get different masses of black holes. So even if we start with the idea of you can have black holes in these specific regions, you can then have black holes smashed together to produce increasingly heavier and heavier black holes. This is also how we think supermassive black holes might be formed. Supermassive black holes that have like 1,000 to 10,000 or even 1,000,000 times the mass of the sun. These could be formed by a lot of black holes gradually merging together and merging together and merging together and gradually getting bigger and bigger each time, leading to these supermassive black holes. This also means that while we have these mass gaps, there are ways where we can fill these mass gaps just by smashing black holes together. But this is all still for stellar black holes, so black holes that are formed by stars that collapse. Now, let me get to the questions here. I think I might have even answered some of the questions as I was going, but let's just double check here. There was a question from Taz. We have supermassive black holes and smaller, relatively stellar black holes. Why the huge gap in between? This is exactly what I was just saying. It's due to the way that black holes are formed. Stars collapsing. We know approximately the mass of most stars. When stars collapse, they can go either to neutron stars or to black holes. Black holes that are collapsing stars will only be maximum around 25 solar masses. Then there's a gap up to 120, and above that you can have different types of black holes forming. So this is why we have different gaps there. All of the things about primordial black holes I'll come back to in a minute, because I'm sticking for now just with the stellar ones. Question from David Howden here. If you bash a few stellar black holes together, can you get one above the maximum mass? Absolutely, you can. And this is how we get higher up mass black holes, is by smashing them together. Hey Sen, great to see you. And thank you for all the comments you keep leaving on the videos. It's always nice to see people leaving comments on the videos. David Howden, I leave inventing a black hole bashing device as an exercise for the reader. Yeah. We do know how to get black holes to smash together, though. You just need to bring them close enough that gravity will do the rest. But probably not something you want to do in a lab. You probably don't want to start smashing black holes together in your lab. It might get a bit destructive. Okay, excellent question here from Ben. How do the atoms/particles bypass the Pauli exclusion principle? So this is a very good idea. Very good question. The Pauli exclusion principle is this idea that subatomic particles can't get too close to each other. At some point, you have some kind of force pushing them outwards. You cannot have two electrons, for example, inhabiting the same space. There's going to be kind of something forcing them apart, and this is what is known as the Pauli exclusion principle. This plays a role in neutron stars, where you can't have the neutrons, which are just formed up of protons and electrons that have been merged together due to the intense pressure. You cannot, the mischief is happening. You cannot have the neutron stars inhabiting the same space, due again to this kind of exclusion principle on a different scale, and this is what gives the neutron star structure. Inside the black hole, however, we have no idea what happens inside a black hole. Our physics, our maths, our equations break down inside a black hole. Now, right inside a black hole is what we define as a singularity. A singularity is a fancy word of saying our equations break down. Once you cross the event horizon of a black hole, the curvature of space-time, the gravitational force is so intense that it becomes very difficult to actually start describing things properly. Then you also run into the thing that black holes are objects described heavily by the gravitational force. Pauli exclusion principle is something that is very much the language of quantum mechanics. Putting together the language of gravity and the language of quantum mechanics is something that is still work in progress. We do not actually know how to put these two together. So it gets very hard to talk about quantum effects inside a black hole, because to do that, you'd need to understand how gravity works on a quantum level, and we are not there yet. But to answer your question, Ben, Pauli exclusion principle is highly relevant inside neutron stars. Inside black holes, who knows? Your guess is as good as mine. We really don't know what happens inside black holes, because that is where our equations break down, and we cannot get any information outside of coming back from a black hole, which makes it very difficult for us to study what is happening beyond the event horizon of a black hole. Okay, comment from James here. I keep hearing the universe is super empty. That is true. Where is all this mass coming from for black holes to be smashing together? Very good question. The universe is very, very, very empty. The closest star to us is 4 light years away, which means it would take you 4 years traveling at the speed of light to find the next star. But inside galaxies, there are billions of stars, which also means there could be billions of black holes left over from the first generation of stars that lived and died. At some point, these gravitational objects are going to meet each other. We're talking about objects that have a huge gravitational force. they're much more likely to pull each other together. All you need is two black holes approximately close, swinging by each other, and then gravity will be like, oh no, we're going to start spiraling, merging, and poof, now you're left with one black hole. So even though the universe is extremely empty, within galaxies, you can get very many merges of black holes. And then if you think about even more massive black holes, the more massive they are, the more likely they are to attract another object that's passing by. So then you can get more objects merging together. Okay, so this was the whole picture for stellar mass black holes. Is there any way to figure out the age of a black hole? Not specifically the age of a black hole per se, but if we can figure out the distance to a black hole, we can figure out approximately its age. The reason for this is the further out into the night sky you look, or the further away you look, the further back in time you're looking, because it takes a while for light to reach us. Light has a finite speed of travel in the universe. It takes a while for it to reach us. So when you look at a galaxy that is a billion light years away, you're looking at what the universe looked like a billion years ago, because that's how long it's taken the light to reach you. So even though we can't date a black hole itself, we can give an age to the galaxies in which these black holes are found, and that helps us figure out how old the black holes are. Okay, so all of this was just intro to black holes. Now let's get to primordial black holes. Now, primordial black holes are a hypothetical, we have not yet found any, hypothetical different way of forming black holes. Now, a primordial black hole is a black hole that, rather than being formed through the whole collapsing star thing, is basically formed by a region of space-time being so dense that it can automatically collapse to form a black hole. This is something that could have happened in the very early universe. This is why we call them primordial black holes, because they're primordial from the early universe. Now, in the early universe, there was a lot of stuff happening, but there were regions of the universe. At this point, we don't have a lot of matter in the universe. At this point, what we have mainly is energy. We have some energy. We have some electrons, some ions, some ionized particles. Sorry, not electrons. We have some ionized particles. We have a lot of energy, and we have space-time. Now, you could have regions of space-time that have more energy and regions of space-time that have less energy. So the idea is one of these regions that is overdense, so more density in the early universe, could directly collapse to form a black hole. Now, imagine this is your space-time. Imagine this is space-time, and your space-time looks like what's in between my two hands here. Now, you see you have regions here that have more energy and regions that have less energy. You have valleys and you have mountains, or troughs and mountains, troughs and peaks. Now, what we're saying here in the case of primordial black holes is one of these regions is so much more dense than its surroundings. So you have the low density here and the high density here. What we're basically saying is this region is so dense that it collapses under its own gravitational force and forms a black hole. Slinky toy came out. So primordial black holes are black holes that don't require a star. They don't require anything else. It is just a region of space-time that is so dense it can automatically collapse to form a black hole. Coming back to the questions here, there was a question from Taz here of, is there any way to figure out the age of a black hole? I answered that one. There was someone else there was a question that I wanted to answer. Where was it? Where was the question that I wanted to answer? It has vanished. There was a question. There it is, from James. Sorry. I keep hearing the universe is super empty. Where is all the mass coming from for black holes to be smashing together? Yeah, I answered that one. There was another one. There was another question that I saw that I wanted to answer, and okay, it's vanished. Maybe I imagined that question. Okay, coming back to that later. Question from Jim here. The accretion disk of stuff falling into black holes which are eating, not all black holes have them, and they don't care, yes, gets hot, becomes plasma, and emits spectral lines which will be redshifted by distance. Absolutely, very, very true. So even though dating a black hole itself is very difficult, all of the matter that is spiraling around a black hole and falling into it, which is what we call an accretion disk. Not every black hole has an accretion disk. Some black holes do. Most black holes do. Hang on, let me get my... I moved my plushie. It's out of reach. Okay, black hole plushie. You can imagine this is a black hole. Around the black hole, you have all of this accretion disk, which is matter that is gradually falling into the black hole and getting sucked into it. This is the accretion disk. I have a black hole plushie. It has a white hole on the other side. We're not going to go into that today, but black hole plushie, all of the matter falling in. This accretion disk, this is stuff that the black hole is eating. This gets really hot and emits specific light, or light at a specific frequency. By measuring this, we can kind of get an idea of the distance to the black hole, which again gives us an idea of the age of the black hole. So that is another way we can go about asking things like the age of a black hole, but it again comes down to measuring the distance. Thank you for the comment there, Jim. Yes, so excellent question here from David Howden. What do you mean by the density of space-time? You think of density as mass divided by volume, which doesn't seem right here. Exactly. Now, what we're saying here is there are regions where there is more energy and regions where there is less energy. Now, here in energy, we're talking about kind of this primordial stuff that was in the universe. Really early on, we're talking primordial black holes formed maybe a few seconds into the universe, a few seconds after the end of inflation, or even during inflation, which puts them about 13.8 billion years ago. Whereas stellar black holes are ones that would have formed after the first stars. So first you need to form stars, you need the stars to reach the end of their lifetime, and then collapse to form black holes. So stellar black holes, we're talking things that are formed in the last 8 billion years. Primordial black holes, we're talking about things that were formed 13.8 billion years ago. Now, what we mean by the density of space-time is if you imagine space-time should be approximately flat. We know space-time is approximately flat, but instead of being completely flat, there are tiny ripples. So instead of your space-time being completely flat, it's maybe a bit more scrunched up paper-like. I just attracted the interest of a cat doing that. So then you have regions where you have kind of valleys and mountains, because space-time itself is not completely flat. That was the last page of my notebook, by the way. I didn't just like scrap up my whole notebook. So the question is, where do these overdensities come from? Which is exactly the thing I wanted to answer. Now, we know that the very early universe was not completely smooth. Basically, what we believe happened is the universe had tiny quantum fluctuations. Quantum fluctuations are just ripples, because there's nothing in physics that is completely flat, perfect. There's always some perturbation or some variation, some change. And usually, if you go back to the very early universe, you're going to be dealing with the quantum stuff. And there you basically have just tiny quantum fluctuations. Then inflation happened. Inflation is this period of exponential expansion whereby everything in the universe is pushed outwards extremely quickly. This means that your tiny overdensities at this point get stretched and get magnified. So we expect the early universe to be slightly bumpy, and during inflation, these bumps are stretched outwards. Now, what we're saying with primordial black holes is that these bumps could directly collapse into forming a black hole without having to wait for stars being formed. You have a region where you have overdensity. The reason you have an overdensity is because you have a slight dent in space-time, which allows more stuff to fall in, more energy to fall in. This is going to form an overdensity. This overdensity can collapse to form a black hole. Now, we're pretty sure these overdensities existed. We have very, very, very good piece of evidence for them. I'll come back to the questions in a sec. We have one very good piece of evidence for these overdensities and underdensities in the early universe. And you'll know what's coming. I can't do a stream without it. Even if we're talking about primordial black holes, this has to appear. This is the cosmic microwave background radiation, or CMB for short. This is the oldest light we have in the universe. It is a snapshot of what the universe looked like 380,000 years after the end of inflation, or about 13.5 billion years ago from our perspective. Now, what happens here, this is a picture of the light all around us, the oldest light in the universe. So in the early universe, you have three main components. You have protons, you have electrons, you have photons, which are particles of light. Because the universe was so hot, all of these things were constantly interacting, constantly bumping into each other. Light could not travel freely. As the universe started to cool down, the protons and the electrons combined together to form the first atoms in the universe, at which point the photons can break away. They no longer have to travel with the other two. And the photons, the particles of light, start traveling freely throughout the universe. They have been traveling freely ever since. And today they make up the cosmic microwave background radiation. So this here is a snapshot of what the universe looked like 380,000 years after the end of inflation. But as you can see in this map, there are orange spots and there are blue spots. The orange spots are slightly hotter photons, particles of light. The blue spots are slightly colder ones. Based on how many orange and blue spots there are, we know things like how old the universe is, what is inside the universe. We know that from this here. But where did the blue and orange splodges come from? Why are there photons that are hotter and why are there photons that are colder? And the answer to this is because the universe was bumpy. The early universe was very bumpy. There were these overdense and underdense regions. The overdense regions now are the blue photons because the photons lost a bit of energy climbing out of this overdensity before coming to us. Which means the CMB, the cosmic microwave background radiation, gives us proof that in the early universe there were overdensities and there were underdensities. Otherwise, we would not be able to explain this picture. So we already have the right conditions for primordial black holes to form. The same mechanism that gave the bumps to the CMB could have resulted in primordial black holes forming. So this is really cool because what we're saying here is that to have primordial black holes, we're not asking for anything new. We're just saying the universe was bumpy and these bumps could have collapsed to form a primordial black hole. See the comment here of wasn't expecting the CMB? You know me. Of course the CMB is going to appear. It's like I'm contractually obliged to show the CMB. Also, I have my CMB beach ball right behind me just in case we need more CMB. But I doubt I'm going to need that today. Also, just fun fact, if I'm preparing a topic, I often have bullet points that I'm going through to keep me on track because otherwise ADHD brain is going to take me all over the place. But amongst the bullet points, there is always a comment of show CMB here. So that's how you know CMB is going to appear. That said, my bullet points I accidentally closed like 2 minutes into the stream, so I am just kind of winging it at this point. But I have the bullet points somewhat memorized because I was finishing them just before the stream. Okay, so excellent question there, Paul. I will get to that. I have not covered it. So just to recap what I said so far. 2 different ways you can form black holes. There's the standard picture where you have a star reaching the end of its lifetime, it collapses, it forms a black hole. And then you have the primordial black holes. Hey, I found my bullet points again. Then you have the primordial black holes, which are, instead of going through the whole stellar evolution phase, you have a region of the universe that can directly collapse to form a primordial black hole. So this would mean that you could form primordial black holes already in the very, very, very early universe without having to wait for stars to form and things like that. So you have these 2 different approaches to forming black holes. I'm just putting my phone away because it buzzed and that caught my attention. I should not have my phone open next to streams. Okay, so going to go back to the questions and then I'm going to tell you why primordial black holes are so important. Why does it matter if we can have this overdense region of the universe that collapses to form a primordial black hole? Comment from Taz, if you did not see the black hole plushie, it's here. It appeared a few minutes ago. Black hole, white hole plushie. I have my whole arsenal of props today. I have this one. I have the Slinky toy. It's all out here. Do not cover the vents of my laptop. That would be a bad idea. Okay. Brain is braining. Question from Ben. Would it be possible for space inside a black hole to expand faster than light, which would lead to black holes forming inside it? The problem here is that inside a black hole, space-time is no longer expanding because it is extremely dense. It is so dense that there's just such a huge gravitational force that you'd overcome anything causing space-time to expand. So we know that currently the universe is expanding, space-time is expanding, but inside a black hole, gravity wins. Space-time is not going anywhere. It's stuck there. It can't expand because of the gravitational force. I see we have another very cool question here. I'm talking about primordial black holes. Question from James. Shouldn't we also have primordial neutron stars? Hypothetically, yes, but if we consider that a neutron star, so when we talk about a star forming, collapsing, becoming a black hole, what we have inside the star is hydrogen, helium, all of which are formed of protons, neutrons, electrons. That gives you the starting point for a neutron star. You have protons, you have electrons, you add a lot of density and a lot of pressure that you can fuse these together, you get neutrons. However, if we're talking about primordial black holes, this predates the formation of neutrons, it predates the formation of protons. At this point, it's just space-time itself that has collapsed. So you cannot have a primordial neutron star because primordial black holes would form before neutrons, before protons. They would be a few seconds or less into the universe that these things would form. At that point, we don't yet have neutrons, we don't yet have protons, which is what you would need to have a neutron star. So we cannot have primordial neutron stars. But it is cool to think about what would that look like. Okay, so I know there were a lot of questions about supermassive black holes. I want to get to that. There's also the question from Paul here. Oh, it was not yet covered. If you see a small black hole, how do I know if it's primordial instead of an evaporating black hole? I'm going to get to that later on as well. But I want to tell you why we care about supermassive black holes. And then I'm going to go through all the questions, because there were a few that I said I'll come back to that I'm going to come back to. And again, we still haven't got to the main topic today of the new results, but we can't get to new results before discussing old results and setting the scene. So there are several reasons why we care about primordial black holes, or why primordial black holes could be interesting. Now, one of them is, I mentioned before, we're not completely sure how supermassive black holes are formed, because even though we have this idea that you can have black holes smashing together to form gradually heavier and heavier black holes, getting a black hole that has 1,000 times the mass of the sun, or even 1,000,000 times the mass of the sun, would take quite a long time, especially if you need to wait first for all the black holes to form. Primordial black holes allow you to get a head start on this, because it basically gives you an extra few billion years during which you can already have black holes forming, smashing together. You can have primordial black holes forming, smashing together, before even the first galaxies have appeared. So this allows you to kind of get a head start on building up enough mass to have supermassive black holes. So one reason primordial black holes are interesting is because they could explain the origin of supermassive black holes, because it just gives us a head start. It means you can already form your primordial black holes a lot earlier on. Another thing that is interesting about primordial black holes is they don't have the same constraints in terms of the mass that we have with stellar black holes. Now, I mentioned before, stellar black holes, if it's a black hole, it's going to be between 5 and 25 times the mass of the sun. If you go over 120, it's a supermassive black hole. If it's a neutron star, it's between 1 and 2 solar masses. You don't have the same constraints with primordial black holes. This means you can form primordial black holes of any mass, because you don't need to care about the whole stellar evolution. You don't need to care about star dynamics. So you can form primordial black holes of any mass. And if you form them early enough and let them smash together, they could be any mass today. So this is a very, very cool thing, that primordial black holes allow you a much bigger range of masses for black holes to exist. But one of the most important reasons why we care about primordial black holes comes back to dark matter. Now, I haven't talked about dark matter yet, so let me bring up my CMB, and we're going to go from here. Now, so I love this topic today because I'm going to cover so many cool things. Okay, so this was the CMB, the cosmic microwave background radiation, and I mentioned that based on the cosmic microwave background radiation, we know what the universe is made of. So we know that the universe has 3 main components today. Everything you see, everything you're used to, everything from my slightly suspiciously calm cats to my tea mug to all of my props to Rami, we are just normal matter. Hey, Ian, great to see you. Haven't seen you in the chat in a long time. Really nice to see you drop by, Ian. Okay, so all of this stuff is normal matter. Normal matter only accounts for just under 5% of the energy budget of the observable universe. Then you have another 26% that is in the form of dark matter. Dark matter is this weird type of matter that interacts gravitationally but does not interact electromagnetically. This means that dark matter is essentially invisible. It interacts gravitationally, it holds galaxies together, but it is very much invisible, which means we can't see it and it's very hard to study. Then there is the remaining 69%, which is in the form of dark energy. Now, dark energy is this weird type of energy that is driving the accelerated expansion of the universe. It's pushing the universe outwards, and we don't know much else about dark energy. That's basically everything we know about dark energy. But this means that everything we're used to in the universe, everything that we can study, is only 5% of the energy budget of the observable universe. What I want to talk about now is this big chunk, this 26.2% dark matter. Now, we know that dark matter has mass. We know that it's invisible. We don't know much about dark matter. We don't know what dark matter is. There are many, many, many different options. Now, we know that dark matter cannot be formed of stellar black holes because there just aren't enough black holes in the universe to explain all of the effects we attribute to dark matter. However, you could have primordial black holes being the dark matter. So one of the main reasons that people are interested in primordial black holes is because they are a dark matter candidate. So you could have, if there are primordial black holes, they would be invisible, they would interact gravitationally. Sounds a lot like dark matter, and if it quacks like a duck and looks like a duck, it's probably a duck. So if primordial black holes exist, they would be dark matter. The question is, would there be enough primordial black holes to be all of the dark matter? And that is a big question. So the reason why we care about primordial black holes so much is because they could help us understand dark matter. They could help us explain where supermassive black holes come from. Very cool things like that. So they could solve a lot of open questions in physics, and they give us a whole new range of stuff to play about with in terms of masses. Okay, and I'm going to pause here and I'm going to go from the top through the questions because there were some questions that I wanted to answer after I'd introduced the whole idea of supermassive black holes. So where we are right now, and primordial black holes. So where we are right now, we have these hypothetical primordial black holes formed in the very early universe that could explain supermassive black holes. They could explain dark matter, but I'm going to keep emphasizing the word hypothetical, and I'll come back to that in a minute. But taking it from the top, there were some questions that I wanted to answer. There was a question from James that primordial black holes and dark matter, as I said, those things are not necessarily as disconnected as we thought they would be. Okay, question from Prath, what asked quite a while ago by now. What if the reason we don't see what we define as primordial black holes is because all of them merged over time to form supermassive black holes? So this is a valid point. If you had formed primordial black holes in the early universe, would they still be of the same mass, or would they have all formed into supermassive black holes today? Are all of the primordial black holes now in the form of supermassive black holes? And that very much depends then on how many primordial black holes you want to make, which depends on your specific model and what you would actually want to then do with your primordial black holes. And again, just to recap, the reasons we care about primordial black holes are because they could solve some open questions, but also because we have a mechanism to explain their existence already. We know the universe was bumpy. We know this because of the cosmic microwave background radiation. Primordial black holes fit in very nicely within our theories. Okay, I answered that question. There was the other question from Prathio, like the follow-up. What if supermassive black holes are primordial black holes because the general density of matter in space was significantly higher pre-expansion? That is also the thing. If you can form primordial black holes of basically any mass with some limits, the upper limit that we consider is usually around like 10 to the 20 solar masses, which is a lot. So hypothetically, yes, you could already form primordial black holes as supermassive black holes, hypothetically. And again, I will come back to this. Okay, I think we answered that question about bashing black holes together. We answered Pauli principle. I'm doing quick fire questions. As always, if you feel like I haven't addressed your question, please feel free to ask it again. But I think we covered a lot of those questions. Then we talked about the density. Yes, I'm just catching up with the questions. There have been a couple questions about, do black holes have spin? How do we know the direction of spin? Now, one of the things that we have about black holes is they are most likely spinning. Now, a lot of objects in the universe are spinning. One way we can see this quite nicely with black holes is the accretion disk. The accretion disk is usually spinning around the black hole as well. Now, the reason why a lot of objects in the universe are spinning and black holes are no different is because it is just much more likely to have an object with spin, and then you have conservation of angular momentum. An object that is spinning is not going to randomly stop unless there's friction or something slowing it down. Planets are spinning, stars are spinning, galaxies are spinning, because once you form an object, even if it has the slightest bit of angular motion, it will start spinning. And the chances of forming an object with precisely zero angular motion is rare. So as far as we know, most black holes are in fact spinning, which is true also for primordial black holes. There's no reason why they wouldn't be. So yes, we assume that they are spinning. How do we know the direction of spin? Usually from matter, the way that matter falls in on top of it. If the black hole is spinning counterclockwise, it would be very unlikely for the matter around it to spin in the opposite direction. So usually everything spins in the same direction. So we can figure out which direction black holes are spinning in, based on the accretion disk. Okay, I'm just doing quick fire answers to the questions. Again, if you think I haven't answered your question, ask me again and I will try to answer it properly. Okay, there was a question about CMB and old radiation, but it's a bit far away from the topic, so I'm going to ignore that one for now. Sticking with the question of spinning black holes, there was another comment from Taz here. Is it essential for black holes to have spin for it to create an accretion disk? You can still, to have the actual disk, yes. So if you had a perfectly non-rotating black hole, which we don't think happens, but if you did have that, matter would still fall into it, but it wouldn't spin around it in an accretion disk. So to have an actual accretion disk around a black hole, you do need some amount of rotation. Sticking with this, comment from Taz, if we see a galaxy spinning in one direction, but black hole spinning in another, can we deduce that the black hole did not have origin in the galaxy? Not necessarily. Like, even though objects are more likely to spin in the same direction, it doesn't always happen. Like, one of the planets in the solar system is spinning backwards. I believe is it Uranus that is spinning backwards, or is it Neptune? I think it's Uranus. One of the planets is spinning backwards. So even though our Milky Way is rotating in one direction, most of the planets spin in the same direction. One of the planets spins in the opposite direction. So you could also have a whole galaxy moving in one direction and a black hole spinning in the other direction, just based on how it was formed. And that is a possibility. So yes, that can happen. You can have things spinning in different directions. That is perfectly possible. It doesn't necessarily tell you that the black hole came from a different galaxy or did not originate in the galaxy. Okay, comment from Ian here. Super duper cool. Thank you, Ian. I'm glad you like the topic. Your daughter sleep under posters of black hole evolution from Kurzgesagt. That is so very cool. This is also a Kurzgesagt merch. It has a nice logo here. For anyone who doesn't know, Kurzgesagt is the second best science channel on YouTube after mine, of course. They do amazing science videos with very cool animations, and they have lots of merch. Highly recommend getting their merch because it is good quality merch. And you get cool things like black hole posters. I think, yeah, Venus also spinning in the opposite direction? I don't think Venus is spinning in the opposite direction necessarily. Uranus is, yes. And there's also one that's spinning on its side. It's fun. Okay, I think I just did quick fire answers to the questions. I don't have any pending in my brain now. If there's something pending, do let me know. A comment from Paul here, a question from Paul. Am I right that primordial black holes would be everywhere rather than specifically only within galaxies? If that's true, doesn't that break the model of where dark matter is supposed to be distributed? Very good question there, Paul. Now, of course, if you have primordial black holes forming in the overdense regions, that doesn't necessarily mean they're forming inside galaxies, which is where stellar black holes are forming. However, these overdense and underdense regions, which give us like each will give us the CMB, the same overdense regions that produce this also set the seeds for galaxy formation. So while it's not one-to-one, you are much more likely to have clusters of galaxies overlapping with the blue spots here than you are with the red spots. It is not one-to-one because things move and things get distorted, but the same overdensities in the early universe that give us the cosmic microwave background radiation set the seeds for galaxies, and they might also set the seeds for primordial black holes. So even though then we don't need the stars inside galaxies to form primordial black holes, the overdensities would overlap, and therefore you would still get most of the dark matter inside galaxies because that's where the overdensities were. It's the same mechanism, just inverted, which is very, very cool. Okay, I realize we are on bullet point 3 out of 12. We'll get through them. It's fine. We're going to do this. It's all good. So we know how primordial black holes are formed. We know why we should care about primordial black holes. The question here is, how can they be observed? And I know there was a question from Paul about evaporating primordial black holes or evaporating black holes. So let's get to that. So there are several different ways that we can observe or hope to observe primordial black holes. Now, one cool thing about black holes is that they have what is known as Hawking evaporation. So even though black holes are big, massive objects, they can actually lose mass slightly due to a process known as Hawking evaporation. Now, Hawking evaporation, to be clear, is not taking something from inside the black hole and removing it. That's not what we do. We can't do that. What is happening is that the black hole itself is gradually shrinking due to some particles being created on the surface of the black hole. One falls in, one falls out. You kind of lose energy to compensate this, or to not lose energy. The black hole has to lose a bit of mass. But this means that that black holes in general can experience what is known as evaporation, where they gradually lose their mass in this form of radiation until the point where they get so small that they would disappear. Now, we know that normal black holes cannot disappear, evaporate via Hawking radiation within the lifespan of the universe, because it would take a substantially long time for a solar mass black hole, or one solar mass black hole, to evaporate. It would take about a billion times the life of the universe for a stellar mass black hole or stellar black hole to evaporate. However, primordial black holes, because they can be formed at very different masses, they could be extremely small. They could be a lot smaller than a solar mass, and therefore they could already evaporate. If primordial black holes evaporate, they produce energy. They put this energy into the cosmos, and anything that injects energy into the early universe is going to modify the cosmic microwave background radiation. Based on the fact that we haven't seen these modifications in the cosmic microwave background radiation, we can say primordial black holes probably didn't evaporate in this time period. There's other things that primordial black holes can do. Primordial black holes could, if you have primordial black holes and at some point they've merged together, you're going to have a lot of stray black holes in the universe of specific masses. Now, these black holes at some point might pass in front of distant stars. This creates an effect known as microlensing, where the black hole acts as a lens and affects the light of the distant star. This is something we know happens on a larger scale, where dark matter clusters can distort distant galaxies, and this is how we study the distribution of matter and the distribution of dark matter in the universe. So if you have a huge population of primordial black holes, at some point, you'd expect a primordial black hole to pass in front of a distant star and produce something known as microlensing. Based on the amount of microlensing we have not seen, that allows us to put constraints on the primordial black holes. And there's a lot of different games you can play like this, of if there were this many black holes, you'd see this. We haven't seen this, therefore there's not that many black holes. Now, if we want primordial black holes to account for all of the dark matter we see today, we need quite a few primordial black holes. But then we can play this game of, based on the primordial black holes that I have, or based on the stuff that I haven't seen, maybe I have fewer primordial black holes. So for the last kind of 30 years, there's been this ongoing debate where people will propose a new method or a new system or a new thing for primordial black holes, a new way of producing them, a new way of observing them, and then we don't observe them, and then we can constrain them. A couple years, about 10, 20 years ago, 15 years ago, I would say, people kind of reached a conclusion that primordial black holes cannot account for all of the dark matter. Caveats apply. Question here from James: are primordial black holes formed before or after light is released in the early universe? Before. So in this picture, what would happen is we have inflation. During inflation, or right at the end of inflation, you form primordial black holes. These sit in the overdensities. That is where dark matter is going to pile up. Is it the same? Is it not? That is where stars are going to pile up. That's where you're going to get galaxies. So primordial black holes would be formed in the first few seconds of the universe. The cosmic microwave background radiation is produced 380,000 years later. The first stars would form a few million years later. The first black holes from stars would form about a couple billion years later. So primordial black holes really give you at least a billion years head start on any other type of star in the universe, and it is formed long before the CMB, which is why if you have too many primordial black holes, you would see their impact on the cosmic microwave background radiation. You would see its effect. Because we don't see its effect, we can put constraints. I forgot that I don't really like this infusion. I'm out of my usual tea, and I didn't have any caffeine-free tea left, so instead of drinking something caffeinated, I went for an infusion. It's just not a great infusion. There's a reason it's been in my cupboard for a long time. Mandatory digression about tea, which is also a regular occurrence. So, based on this whole process of we haven't seen black holes doing this, maybe there's not primordial black holes, we've been able to put some pretty good constraints. And I'm going to show you a figure from a scientific paper. There's actually a really nice review paper that came out really recently, like a few weeks ago. Review papers are where experts in the field sit down and write a like 200-page document of status of this thing. And there was actually a very recent status of primordial black holes document, which is amazing. And I'm going to show you a figure. Warning, this is a very complex figure, but don't worry, we're going to walk through it. So this should be coming up on screen anytime now this year. So what this figure is showing us is basically two properties of primordial black holes. On the horizontal line, you have the mass in terms of solar masses. So you see it goes from like 10 to the minus 24 solar masses, which is insanely small, to 10 to the 20 solar masses, which is insanely big. On the vertical axis, we have how much of the primordial black holes, or sorry, how much of the dark matter today is made of primordial black holes. So if you live on the top of this graph, you're saying 100% of the dark matter is in the form of primordial black holes. There's enough primordial black holes to explain all of the dark matter. As you move further down the plot, what you're getting to is the regions where you only have like 10% of the dark matter is formed of primordial black holes, or 1%, or a millionth percent. You gradually, as you go down, you have fewer and fewer primordial black holes, which means you still need other things to explain the dark matter. Now, all of the shaded regions have been excluded by different measurements, which means that say you want 100% of the dark matter to be in the form of primordial black holes, there is only a small region to the left that is clear on the top. Everything else has been ruled out. So this was the status kind of a while ago where if you want primordial black holes to be 100% of the dark matter, you have so many different observations that are telling you, no, this can't be true. So don't worry about this plot too much. The only thing I want you to focus on is the top line. If you live at the top of this graph, that is where you can explain all of the dark matter with primordial black holes. Any part that is colored in with any color has been excluded, which doesn't leave you much range or much region where primordial black holes could explain all of the dark matter. However, people who like primordial black holes don't like this figure and then say that this figure is actually not completely correct, because this figure assumes that all primordial black holes are formed with the same mass. You either form primordial black holes of 1 solar mass, or of 10 solar masses, or of 1,000th of solar mass. And that is not what we expect to happen. So this is assuming a specific mass distribution, and what we actually expect to happen is an extended mass distribution. So just to give you some jargon words that you might have seen in the literature or in pop science articles, if you form all of the primordial black holes with the same mass, it's called monochromatic. If you form it with different masses, it's called extended. So what people have been doing for the last like 15, 20 years is saying, okay, but if I form my primordial black holes across a range of masses, this plot is no longer valid. So there's been a back and forth between kind of the observational people and the theorists who like primordial black holes, where the theorists will say, okay, here's a new way of making primordial black holes that gets away with these constraints. And then the observationists will find another observation and say, actually, no, it doesn't. And this led to the point where it felt like for years you could open up the science news, the science papers, and every week you'd find a paper saying like, primordial black holes are all of the dark matter. And the next week you'd find a paper saying like, no, they're not. Now, this has been an ongoing debate for years. So where we are, primordial black holes, end of 2025, we're at the stage where primordial black holes are super cool. Primordial black holes could explain some or all of the dark matter, but there's a lot of observational constraints that make it very, very, very difficult. So it's always been this game of, do we like primordial black holes as dark matter? Do we not? People have very strong opinions on this, because the people who spent years working on primordial black holes will find new ways to avoid these constraints, and the observationists will find new ways to constrain this, which is super cool. This is how science progresses, right? People really set out to prove what they want to prove. So that was the status circa 5-6 months ago. But there have been a couple things that have happened over the last few years that people have seen have been like, did we find a primordial black hole? Have we found a primordial black hole? And I want to talk today about, or Jim asked me to talk, and I want to talk about two observations that have happened over the last few years, and specifically very recently, that has made people go like, did we just see what I think we saw? Is that what I think it is? Spoiler alert, probably no. But let's get into it. Now, before I get into the new observation, I'm going to take a step back and talk about something I love, which is gravitational waves. Now, before I get into gravitational waves, I think I have addressed some of the questions. Let's just recap here. I know there was another question from Paul that I still need to answer. Let me get back to that. But first, another question here from Paul. Am I right that primordial black holes would be everywhere? Yes, I answered that one. Absolutely answered that one. Yes, thank you. There was the other question of, if you see a black hole, before I get into the new observations, if you see a black hole, how do you know if it's primordial or if it's stellar? How do you know how it was formed? And the short answer is we don't actually know. Just by looking at a black hole, you can't really know its story. So just by looking at a black hole, you can't necessarily figure out if it's stellar, if it's primordial, but there are some telltale signs. For an example, I mentioned before that stellar mass black holes have specific constraints on the mass. If you find something that doesn't fit within that mass, it might be primordial. Stellar mass black holes cannot be evaporating today. They haven't had long enough. If you see a black hole that is evaporating, it has to be of primordial origin. So there's a few of these caveats. While if you just stare at a black hole in general, you probably won't know how it was produced. There are some telltale signs that give it away. For an example, if it's evaporating, depending on the mass, then you can go about saying, like, well, maybe this is primordial, maybe it's not. Now, ideally, you need a lot of observations in order to do population statistics, and that allows you to distinguish between the cases. So, before we jump into the new observations, gravitational waves. Love gravitational waves. Get to talk about CMB, gravitational waves, dark matter, all disguised as primordial black hole topic, but you all knew that was going to happen. So, gravitational waves are ripples in the fabric of the cosmos produced by dramatic events. For an example, black holes smashing together. Anytime you have an object with mass moving through the universe in a non-symmetric way or non-standard way, you will produce ripples in space-time, which are called gravitational waves. Now, for an example, if I'm spinning here on my chair in a perfectly symmetrical way, I am not producing gravitational waves because it's symmetrical. However, if I start doing this wildly on my chair in a non-symmetrical way, and I say that my hands do the same thing always, that produces gravitational waves because I'm distorting the space-time around me. Gravitational waves are produced by a lot of things, but especially if you have two massive objects that are going to find each other, start in spiraling and crash and produce gravitational waves. So we've talked a lot today about black holes smashing together so that you get bigger black holes. This is a process that is going to produce gravitational waves. It is going to produce ripples in the fabric of space-time. This is something that is predicted by general relativity over 100 years ago, and it is something we have measured over 320 times by now. So we have a couple of ground-based detectors known as LIGO, Virgo, CAGRA is online as well, which are all detectors looking for gravitational waves. So they're basically underground, some in the US, Virgo is in Italy, CAGRA is in Japan. There's Indy 600, which is Indy 600, no. There's one in India coming on soon as well. So basically these detectors have two very long arms with mirrors at the ends. They send lasers back and forth. Based on the arrival time of the laser, you can figure out if anything messed up the distance of these arms. If anything messed with the distance, it's got to be a gravitational wave, because a gravitational wave messes up with space-time. First, it makes things get shorter and fatter, and then taller and thinner. This is a gravitational wave traveling through my hands. So by looking at how space or how distance is changing, using lasers to get incredibly precise measurements, you can figure out gravitational waves. You can measure gravitational waves. LIGO and Virgo have by now measured 300 times black holes or massive objects smashing together and producing gravitational waves. And it is amazing because we did this for the first time in 2016. It's been 10 years. It's been 10 years since the first gravitational wave announcement. Wow. That just hit me. Just suddenly felt very old then. Wow, it's been 10 years since the first gravitational wave announcement. But this is something that is amazing. And by now we've done it over 300 times. I will never get over how amazing it is that we know how to measure these tiny ripples in space-time. Now, usually, because we've had a lot of time to prepare for these experiments, we have a database. We have a database basically saying if you have object A and object B of specific masses and they merge together, this is what it's going to look like. This is what the gravitational wave is going to look like. So then what we do is we look at gravitational waves, we find them in our detectors, and we compare them to our billion entries in our catalog in our library, telling us which one it is. So if we measure gravitational waves, we can pretty accurately figure out how massive the two objects were that crashed together and how far away they were. Now that is it's not ideal. One sec. Cannot lose my voice this week. I have way too much going on this week to have voice issues. I'm sure it's just the dry air or the change in temperature. I know, my body being weird. So once we measure gravitational waves coming from merging black holes or merging objects, we can pretty much figure out how massive the two black holes were and how massive the thing that's left behind is. We have done this 300 times by now. It's super cool. And most of the gravitational waves that we have measured tell us that the black holes are the masses we expected, kind of in the 5 to 20 range or over 120. But there have been a couple that fall in what is known as the mass gap. So we have found a few gravitational waves coming from black holes smashing together where the black holes were about 35 to 40 solar masses, which is a bit more than what we expect from stellar mass black holes. This raised the question of was that a primordial black hole? Currently, the most likely explanation that people have found is that these 30, 40 solar mass black holes were just smaller black holes that merged together. Were they primordial? Were they stellar? We don't exactly know. So, comment from Paul here. I would think you would detect stellar debris or other historical artifacts if something is a stellar black hole if you had good enough instruments. Not necessarily, because once a black hole is formed, let's say stars collapse, you have the black hole. At that point, it's going to start attracting everything that's close by. So unless you get to observe it right after the collapse, it's unlikely that you would still have any stellar debris left over to be able to study because it's going to get sucked up by the black hole. Of course, if you see a supernova, then you know for sure that's a stellar mass black hole that's happening up there. Or maybe a neutron star, but you know it's of stellar origin. So, point being, we can use gravitational waves to study black holes, which is very, very cool. Now, because LIGO and Virgo are so very good at measuring gravitational waves, they now have what is known as the alert system. Because if you have black holes smashing together, you get gravitational waves. But if you have two neutron stars smashing together, you get gravitational waves and you get a burst of radiation. You get a burst of gamma rays, of light, which is very, very cool, because if you can measure both the gravitational waves and the light burst, you can do what is known as multi-messenger astronomy, where you basically study the same event using different information, and that allows you to learn a lot more about the event. So now, anytime LIGO and Virgo measure an event, a gravitational wave, they send an alert, an automatic alert, to a bunch of other telescopes, kind of like point up there, we might have found something worth looking at. So, an alert was posted for LIGO, Virgo, and Kagra on the 12th of November last year, 12th of November 2025. An alert was posted that LIGO and Virgo had found gravitational waves coming from two objects smashing together, and there is a 99% chance that one of the two objects has less than 1 solar mass. This is a subsolar mass object. Now, this was an alert. This was not yet a scientific paper. This has not yet undergone thorough analysis, but it was an alert, and the alert said we might have seen gravitational waves coming from an object below 1 solar mass. Now, just to recap, stellar mass black holes cannot be smaller than 5 solar masses. Neutron stars cannot be smaller than about 1.2 solar masses. How do you get an object that is smaller than 1 solar mass? Primordial black holes. It is the first conclusion, it is the first thought. And if it's not primordial black holes, it's something else that we don't understand. A subsolar mass object smashing together and producing gravitational waves, whatever it is going to be new physics. So this was an extremely exciting thing to happen. But there are some caveats, and I'm going to go through the caveats first. Now, first of all, it has not yet been through the thorough analysis. This was an alert. The alerts are not fact checked. The alerts are just like, we found something, this is our best guess, go. And the alert said one of these objects is subsolar mass at 99% probability. It has not yet been through the thorough analysis. And then there's something that LIGO uses to tell us how much you should believe an observation. And this is the false alarm rate. Now, the false alarm rate tells you basically how long would you have to stare at the sky with LIGO or Virgo in order to find this by chance, for it to be a random fluctuation, for it to be a statistical anomaly. Ideally, you want this to be very low. For a lot of the objects LIGO Virgo have observed, this false alarm rate is like once every 50 years, this would be a false alarm. For this object that they saw in November, the false alarm rate is 1 every 4 years, which means if you stare at the sky for 4 years, you are going to find one of these by chance, and it's a statistical fluke and it is not real data. This is unfortunately a very worrying false alarm rate. It means that this might not be a real signal. So this has not undergone thorough peer review yet. It has not undergone thorough analysis. What the LIGO team are now doing is analyzing this to ideally get more information about the mass and lower the false alarm rate so that it actually becomes more significant. So LIGO has been taking data now for on and off for the last 10 years, which means if this is a random thing that you're going to see on average once every 4 years, and we've finally seen it, it's not yet certain if it's a real observation or if it's just noise. But thank you for all the good questions, Taz, and for stopping by. But if this is a real observation, the most likely explanation might be a primordial black hole, because after the alert went out, obviously all of the other telescopes turned up and looked at the sky, and they didn't find anything. If what we had seen had been like a small star being eaten up by a black hole, there would have been a burst of radiation. We have not seen this. We have not seen the so-called electromagnetic counterpart. Of course, that doesn't necessarily mean it wasn't there. It just means we haven't seen it. But currently, where things stand is there is a small chance that LIGO found a subsolar mass black hole, because there was no electromagnetic counterpart, so it was not a neutron star. And the best explanation we have for subsolar mass black holes is primordial black holes. Now, of course, this led to a flurry of excitement and a lot of popular science articles being like, we have found primordial black holes. Everyone who works on both primordial black holes and on LIGO is being a lot more cautious and saying, sure, it's cool to think about this, but let's just be cautious a minute. Let's please be careful. And also, if I go back to this plot here, this nice plot that I showed you before, this one here, if you look at where the 1 is on the horizontal axis, this would be 1 solar mass black hole. That is kind of what we're saying, that it's just left of the 1. And if you look at that, a lot of the region is already excluded. So what this means is that even if this is a primordial black hole, it doesn't necessarily mean that primordial black holes could account for all of the dark matter. That said, even if we found 1 primordial black hole, it would be huge. Finding 1 primordial black hole already would tell us that primordial black holes are real, they exist, they're a thing. Then we can figure out if they're the dark matter or not. So this observation, it has a very high false alarm rate, 1 in 4 years. But LIGO currently has found something. The code name for it is S251112, which is year, month, date, with a CM after, which means candidate merger, which means it has not yet been verified. The most likely mass for this subsolar mass black hole is between 0.1 and 0.9 solar masses, which is significantly lower than what we can get with a stellar mass black hole. It does not mean that LIGO has found a primordial black hole. What it does mean is that LIGO has found something, maybe, that could hypothetically be explained by primordial black holes. Now, there's a lot of people putting out papers talking, or there's been a couple of papers that have already come out based on this, basically saying, like, if this were a primordial black hole, what would this mean? There was one that was very interesting that looks at the idea of, like, does this mean, are we saying here that we need the primordial black hole to be this mass? Or could there have been a kind of like indirect primordial black hole getting bigger so that the observed mass today does not necessarily correspond to the true mass of the primordial black hole? So people are already trying to find ways to make this signal fit primordial black holes and fit this idea. So it is extremely exciting because if this signal is real and if it is a solar mass black hole, either we need new physics on how stars form, or it's a primordial black hole. In either case, it's new physics. It's exciting. However, the people working at LIGO are being extremely cautious about this, saying, like, it's quite likely that it's a fluke. It is more likely to be a fluke than not. However, that isn't stopping the theorists from having fun with it. There have been three scientific papers already referencing this event, even though the only information we have is the alert page. Again, the LIGO Virgo team have not yet done the full analysis on this. So there is not the full diagrams you can pull up for the mass distribution. There is just the alert saying, we saw this, go look for it. And people are already running with it, and there were a bunch of popular science articles like, is it a primordial black hole? Realistically, no, but why not have fun with it while we can? So this is one of the reasons why people are talking about primordial black holes again. If it's a real signal that LIGO Virgo have found, it might be primordial black holes, which is awesome. But it's probably not a real signal. There's also the thing that even if this turns out to be a real signal, measuring one is not enough. We need to be able to measure a lot in order to do population statistics, to do studies on what this actually means. Nobody in the scientific community will, if LIGO now comes out and says, yes, this is an actual signal, we're not going to the next day be like, okay, we found primordial black holes, we're done. This is going to be the start of a long process, of a long journey, but it's got people talking about primordial black holes again, which is always very, very cool. So definitely keep an eye on this because it is an interesting and exciting result. And it's so cool. And, you know, it might not be true, but what if it is? What if it is? What if this is the primordial black hole? That would be so amazing. I have a soft spot for primordial black holes. They're not my favorite dark matter model. You all know that, Space Dragons. But I have a soft spot for primordial black holes. I think they're a very cool model because they fit so nicely into our CMB theories and everything. It would just be so cool. Then there's something else that has happened over the last few years. We have the JWST telescope, which, as you know, I will never call by its full name because it was named after an extremely problematic person, and NASA should not have named it that. But that aside, the JWST is an amazing, amazing telescope taking really, really cool pictures of very distant objects. Now, one thing that JWST found is what is known as the little red dots. The little red dots appear to be galaxies or stars or objects substantially older than what they should be. Now, they're red, so they kind of look like either stars or galaxies that have been redshifted, which means they are in the red end of the electromagnetic spectrum, which means they're really far away. And these are older, older than all of our models for galaxy formation and evolution. So this is known as the JWST little red dots. The original report said that these little red dots could be active galactic nucleus or AGNs, which are galaxies that have a supermassive black hole at the center, and they would be very, very far away. This could if you had the very, very, very first population of stars collapse into form a black hole, and this could form a supermassive black hole and a galaxy quick enough, you could hypothetically explain this. But every other active galactic nuclei that we have found so far has a lot of X-ray emissions. The little red dots that JWST have found do not have X-ray emissions. So what we're saying here is that JWST has found something that is unreasonably old, older than what we can explain with our standard picture of how stars are formed. Which again leads people to be like, hey, do you want a model for early for early black hole formation? Because I have a model for early black hole formation, primordial black holes. So when the little red dots were found, this is the official name, by the way, they're called the little red dots. When the LRDs, when the little red dots were found, there were a couple people who were like, could this be a primordial black hole? Also very interesting. Now, the problem with the little red dots is we've only found around 30 of them. So these are things that appear in the background of JWST images. There's just these little red dots. Questions. Have we properly accounted for all of the dust things that could make this thing appear redder and therefore older? Could this just be a statistical thing? Because we've only found order 30 of them out of the billions of stars and galaxies that JWST has taken pictures of. So it is not completely clear what these little red dots are. It is not completely clear how trustworthy these observations are, because we don't have many of them. So then there's the question of, what are they? Could they be primordial black holes? Could they be something else? Now, there was actually a study recently that had another hypothesis for what the little red dots are. Now, this study recently said that maybe these little red dots are what is known as a direct collapse black hole. So a direct collapse black hole is a region of the universe that could collapse to form a black hole without going through the whole stellar evolution phase, but in a different way to primordial black holes. For primordial black holes, we're talking about something that was formed in the first few seconds of the universe, when you had your bumpy space-time and your bumps in space-time directly collapse to form a black hole. A direct collapse black hole, on the other hand, is something that could form a billion years into the universe after the first galaxies have started to form. And it's a region where you have a lot of hydrogen, and the hydrogen itself, instead of collapsing to form a star, gets so pressurized, so compact, that it collapses to form a black hole. So while it's the same thing of we're forming a black hole without going through the stellar evolution phase, it's different to primordial black holes. Primordial black holes are space-time itself collapsing about a second into the universe. A direct collapse black hole is a clump of hydrogen inside a galaxy that directly collapses to form a black hole, skipping the whole stellar evolution stage. Direct collapse black holes is not something that we had models for 5 years ago. They were proposed as a way to explain these little red dots, and they do actually explain them really well, because they would set the seeds for bigger black holes to form quickly. You could then have these kind of older red images that are not a stellar black hole, but they are also not a primordial black hole. And currently, this direct collapse black hole scenario does explain the age of these things, and it explains why there's no X-rays, and it explains a bunch of other things. That does not mean it's not primordial black holes. It just means we have an explanation that is potentially more plausible. So the little red dots were a mystery for 5 years. We now have several different explanations for them. The explanation that fits all of the data the best is that this is a direct collapse black hole. So a star that has directly collapsed to form a black hole a region of the universe that has directly collapsed to form a black hole without becoming a star. And that seems to be the prevailing opinion right now. So what are we saying here? Little red dots, which are weird dots that are very red, as the name implies. They're little, they're red, they're dots. We're so good at naming things. Little red dots that JWST has found have multiple explanations, including primordial black holes. The signal that LIGO Virgo have found may or may not be real, But if it's real, it's quite hard to explain without going down the route of primordial black holes. Comment here from Jim. The difference, I believe, is that primordial black holes could be any mass. That is correct. And their proponents think they have very wide extended mass distributions, but direct collapse black holes are always going to be very large. This is very, very true. So a direct collapse black hole does have constraints on how massive it is, because you need the specific conditions of hydrogen, you need the specific conditions of density, and you are kind of fine-tuning it to explain the little red dots. There is a much more constrained way of explaining it. Primordial black holes could have any mass, and therefore they could explain all of these. In order to truly distinguish between these two different scenarios, what we need is more statistics. So we need more little red dots, because doing data with 30 fuzzy images is not really, or doing science with 30 fuzzy images, it's not a lot of data to go on. Now, because, as Jim was saying here, if you have a direct collapse black hole, they're going to have a specific mass, which means these little red dots should occur more frequently. We should be able to see more of them. Primordial black holes give you a whole range of these. They shouldn't all be little red dots. You might have different types of these galaxies that are equally old or differently old, depending on the mass of the primordial black hole. Both are possible options. Currently, it seems like the direct collapse black hole fits the picture better than primordial black holes, but it does not rule out primordial black holes. And again, the proponents of primordial black holes will tell you that you can change the mass distribution, you can change the time, you can change the production mechanism very slightly. There's a lot of things you can play about with primordial black holes to get them to fit the data. But have we found evidence for primordial black holes? Not yet. Have we ruled out primordial black holes? Also not yet. So just coming back to where we started here, then why can primordial black holes have any mass? They can have any mass because you basically just have a region of the universe that is so dense it can collapse to form a black hole 1 second into the universe. There are no real constraints on how massive this is. Different models of primordial black hole, like depending on how quickly they're formed, how exactly they formed, how did this region of the universe collapse, why was the universe bumpy, depending on all these factors, you will produce primordial black holes with different mass. In some models, you will produce primordial black holes of several masses. You produce a range of them. But there is a lot more freedom in your modeling to play about with the mass, which allows you to get many different possible masses for primordial black holes. Stellar mass black holes have constraints coming from stellar formation. So stellar black holes have to deal with the whole thing of stars being formed and dying to produce a black hole. Direct collapse black holes have to deal with the whole thing of having enough hydrogen in the right region to produce a direct collapse black hole. Primordial black holes, because we're talking about something that happened hypothetically a couple seconds into the universe, we have a lot fewer observations of that time period, which means there's a lot more freedom to play about with what was happening in that time period. To recap, primordial black holes are an extremely cool model that could help us explain things like where supermassive black holes come from, what is the dark matter. They are something that occur naturally in very many models, and they fit very well in our picture of explaining why there are temperature differences on the cosmic microwave background radiation, why there are different galaxies. Primordial black holes fit in with this very naturally. Primordial black holes would have some signatures that make them very distinguishable from normal black holes. Based on all the evidence we have so far, we have not yet found primordial black holes, and we've been able to put a lot of constraints on what primordial black holes could look like and what they could do. However, we have not ruled them out. And there are some recent observations that if you like primordial black holes, you'll be excited by these recent observations. If you don't like primordial black holes, your response will be, okay, let's go rule out another region of mass. Let's go rule out another primordial black hole model. It's exciting. It's exciting, and it feels like this model just doesn't want to go away. Anytime there's an observation, it's like, no, this is not primordial black holes, the theorists come up with a way of like, but what if it is? Have you considered that it might be? And this has been going back and forth for years. This debate is not going to be settled overnight. In my personal opinion, the little red dots are probably not primordial black holes. The LIGO observation, I really hope it's a real signal. Based on the statistics, I don't think it is a real signal, but if it is a real signal, it is incredibly cool. And even if it's not a real signal, it's still cool because it's letting us have these conversations. It's giving us an excuse to talk about these things again. Comment here from Ian, this whole JWST finding that you're describing is thoroughly fascinating. Thank you, I'm glad you agree. Can only imagine the conspiracy theories on age of the universe. Absolutely. You know, the first little red dots were found already 4 years ago now. The amount of theories of have we messed up our age of the universe? Do we need to revisit cosmology? Do we throw it all in the bin? It's amazing. There are possible explanations, but there's a lot of fun to be had. And this is how science works, right? You find something new, you find something unexpected, and then it's all hands on deck. Let's figure out what this thing is. And even if it goes away, you had fun in the meantime. And that's how we do science. You have your model, your data says no, then you try a different model, data says no, but then occasionally the data might say yes. And that is when it gets really fun. Just following up here, a comment that Jim is saying, one of the characteristics of most of the little red dots is that their black holes weigh more than all of their stars. They are indeed the heaviest seeds. How does the black hole weigh more than the stars, all of the other stars in the galaxy? If the whole thing appears to be 12 billion years old, where did that black hole come from? How is it so massive? How did it have time to get so massive? These are the questions we don't yet know the answers to with the little red dots. Where did they come from? How are they so massive? Are they that massive, or is our data wrong? These are the questions that we don't know the answer to. The little red dots are super fascinating. We don't know exactly what they are. There are competing models. Whatever they are, they challenge our theories of physics. They challenge our theories of cosmology. Because either we don't know how old the universe is, which would be very scary, or we don't know how galaxies form, which would be very scary, or there's a whole new way of making black holes, which would be very interesting and slightly scary. The little red dots are exciting. They're cool. We don't know what's going on. But the biggest problem is we don't have enough data to know what's going on. So until we get more data from JWST or other experiments about the little red dots, there's not a lot more we can say about them. There's very cool, very, very cool scenario. We just don't have enough data. So, questions. What's next for primordial black holes? Where do we go from here? Now, a lot of you know that I work on an upcoming space mission called LISA, the Laser Interferometer Space Antenna. And I got the question in advance of, is LISA going to be able to tell us anything about these observations? Is LISA going to be able to find subsolar? My slinky got tied up, in case you were wondering what I'm doing. I will fix that later. So can LISA, this upcoming space-based gravitational wave mission, tell us anything about subsolar mass black holes? No, unfortunately, no. LISA is looking at a different frequency range. It is more tuned into supermassive black holes than tiny black holes. So it goes in the opposite direction. LISA is a huge improvement on LIGO in terms of frequencies, but it's a different frequency range. It's looking at something else. LISA will not be sensitive directly to subsolar mass black holes. So in that regard, LISA, this upcoming gravitational wave mission, will not say anything about subsolar mass black holes. However, if you have a population of primordial black holes, let's say we've made primordial black holes in the early universe. Let's say these primordial black holes have been around for 13.82 billion years, and they've been gradually merging together. Because you have enough black holes, they're going to gradually merge together. This is going to produce a background of gravitational waves, a stochastic background, which means gravitational waves in every direction you look, very, very tiny, behind everything else. These gravitational waves is something that LISA might find. So one of the things LISA is looking for, it's zoomies time. My cat has just got zoomies. One of the things that LISA is looking for is this background of gravitational waves. If we find a background of gravitational waves, yeah, you can all tell that this slinky is really irritating me. I'm leaving it alone, but it's there, and now it's here. Yes, so if LISA finds, there we go, fixed it. If LISA finds these primordial gravitational waves, this background of gravitational waves, then there will be a whole debate of, did this background of gravitational waves come from primordial black holes, from other physics like the physics I work on in the early universe? What did it come from? So while LISA will not be sensitive to subsolar mass black hole mergers. It could still shed light on primordial black holes by finding the ripples left over by a population of primordial black holes. There's also, we're getting more data from LIGO, we're getting more data from Virgo, from Kagra. So there is more hope of finding gravitational waves coming from subsolar mass black holes. There's also things like if primordial black holes exist at some point, maybe they should evaporate. We can look for this. We have different telescopes looking for flashes that could come from these things. The Nancy Grace Roman telescope will turn on at some point. The Vera Rubin telescope is incoming soon. All of these will help us find things like fast radio bursts or active galactic nuclei, which could all help us shed light on things like primordial black holes. So, primordial black holes are an extremely cool model that doesn't seem to want to go away. It could explain the origin of supermassive black holes. It could explain dark matter. It fits nicely within our theories. However, we have not found any clear-cut evidence for primordial black holes yet. But there are some potentially interesting signals that we should keep an eye on. My personal opinion here is that primordial black holes are very, very cool, and finding them would be amazing. I just don't think we've done it yet. But the little red dot mystery is not completely solved, and this new thing that LIGO may or may not have found in November is worth keeping in mind. Realistically, it normally takes LIGO about 5 to 6 months to produce a science paper on an observation if there's an actual thing. So between the alert and the science paper, there's usually 5 or 6 months. If you count that this was measured, the alert went out on the 12th of November. November, December, January, February, March, soon-ish. I expect pretty soon there will be a statement from LIGO about whether this observation was real or not. But if it's real, it's amazing. If it's not real, it's still got us excited about primordial black holes again, and that is very, very cool. Okay, we've gone through all my bullet points. Only 7 minutes over time. Not too bad. So, as I mentioned at the beginning, this was a topic request by Jim. Jim asked me to talk specifically about the little red dots and the subsolar mass black hole, but that required all of the backstory of what are primordial black holes, so we went on a lot of tangents. This was a super fun topic, I think. I hope I got you all excited about this. It is a very fun topic. Primordial black holes are an amazing thing. If we ever find primordial black holes and we verify it, it will be a game changer for physics. Even if we find that primordial black holes only account for 1% or a fraction of that of the dark matter, it would still be so cool. Comment from Jim here. You have to go meet family obligations. Thank you for joining. Thank you for the topic, Jim. This was super fun. And don't worry, I'm just wrapping up. Thank you for the topic request. And please go enjoy the rest of your Sunday. And thank you for getting up at 8 a.m. for this. Okay, so primordial black holes are super cool. If we find them, that would be amazing. If we don't find them, it's still fun because it gets us talking. It was a stellar topic. I appreciate the pun, Ian. Thank you. As you know, I'm a huge fan of stupid puns, and I'm a huge fan of science puns. Okay. Thank you, everyone, for all of the questions, all of the comments. I think I addressed all of the questions that came up. If not, now's your chance to shout at me in the comments and be like, you missed an important question. But things I want you to take away from this. Primordial black holes are cool. They may or may not be real, but they're cool. LIGO is doing cool stuff. JWST is doing cool stuff. And stay tuned, because there might be an update for primordial black holes at any point soon. I don't think we're going to wake up tomorrow to the headline, primordial black holes found. But as always in science, slow and gradual progress, and maybe someday we find primordial black holes. Also, I love this topic because it allowed me to talk about the cosmic microwave background radiation, about dark matter, about gravitational waves. It really does tie together so many topics. And that is always fascinating. Did you lose your... and it's under the sofa again. He's just lost his favorite toy under the sofa again. Okay, so if you thought this was a fun format for the stream, you can request the topic too. Go to cupofcosmology.com, go to the section Getting Involved, and there you can find the instructions on how to request the topic. To be clear, please don't go ahead and do a donation and then tell me a topic, because I might not agree to every topic. Contact me first. If you want to request a topic, contact me, and I'll dedicate a whole stream to the topic of your choosing in exchange for a small donation to charities that support people getting better access to science and technology, and in general, different STEM fields. The stream that this topic today, the donation went to OSTEM, Out in STEM, which is an organization helping queer people navigate STEM. So thank you for doing that, Jim. One topic to bind them all, indeed. God, yes, the topic to bind them all. Feels like primordial black holes is a good topic to bind them all together. Okay, so next week, there will not be a Cup of Cosmology. I'm at an art festival. I'm still figuring out my plans, but I'm at an art festival both Saturday and Sunday. I will not be doing a stream, but I should be back 2 weeks from now on the 14th. And then I'm going to take 15th, sorry, on the 15th. And then I'm going to take 2 weeks off because I'm hosting a party, I'm traveling, my March is insane. But Cup of Cosmology should be online 2 weeks from now. That is Sunday, 15th of March, at the same time as always, which is 8 p.m. if you're in Finland, 7 p.m. if you're in mainland Europe, 1 a.m. if you're on the west coast of the US, 1 a.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US, 8 a.m. if you're in Hawaii. Wherever you are, there's a time zone converter on cupofcosmology.com. I know time zones can be confusing for many people. If you go to cupofcosmology.com, there is a time zone converter where you can figure out when the next stream is in your own time zone. But if you want to make sure you don't miss any streams, be sure to subscribe to the channel, either on YouTube or on Twitch. Subscribe, and then you can be notified just before I go live. So then you never miss a stream. And if you haven't done so already, please like this video, leave a comment, interact, leave a comment after the video is done, interact in the live chat. All of it really does help boost engagement, which apparently is stuff that the algorithm likes. The YouTube algorithm gods like those things. My cat is looking so upset because he's lost his favorite toy under the sofa again. I just rescued all of the toys today. Okay, so thank you everyone for joining. Thank you for the questions. This has been super, super fun. I've really enjoyed all of the conversations. This has turned into a bit of a long stream, so wrapping it up. Thank you everyone for joining. This has been super fun. No Cup of Cosmology next week, but I'll be back in 2 weeks and I hope to see you all there. And I hope in the meantime, you'll take care of each other and stay curious.